Can everybody hear me? Okay, all right. So as Paul introduced me, I'm Pavan Agrawal, and I am a high school student from Houston, Texas. So, so recently I had an awesome opportunity to work as a full stack developer in a local business near my house. Through this job, I was able to gain a lot of experience with like serverless tech, non-serverless deployments, and Python, JavaScript in general. Also, if you guys want to follow me on Twitter, there's my handle. I have one follower right now, so if you guys want to be the second or third, please join me. Okay, so before I begin this talk, I want to give the disclaimer. I'm only going to be focusing on the style of serverless that involves deploying pure code to cloud providers. I know GCP recently came out with like Cloud Run that allows you to do serverless Docker containers. This is not going to be that. This is just pure function code. Okay, so I know that we had a good talk about serverless programming before this, but I just want to give a quick overview about what serverless programming is. So for starters, it's actually not serverless. No, cloud providers didn't figure out how to bang some rocks together in the cloud to generate some magical output. Your cloud code is still running on normal everyday servers in the cloud. In reality, it's just more of a fancy abstraction. I think this meme does a pretty good job of explaining serverless. It's just a bunch of abstractions layered over abstractions. So to start the abstraction process, we're getting an abstraction over the platform. You're not dealing with, oh, is this Python runtime secure? Is it completely patched? You're not dealing with the scaling of the abstraction either. Usually, when you provide code to the serverless platform, they are implicitly giving you a contract saying that they will increase the number of instances running your code at any time in order to ensure that everybody has a good user experience. Also, they're abstracting the runtime and the state so you don't get to persist any data on the servers running your code. In essence, you're providing a piece of code to a cloud provider and expecting them to manage it, the scaling of it, and serving of it in order to keep it updated, patched, and deployed for everybody. Most cloud providers already have really great serverless runtime platforms. AWS has the Lambda platform, which has been around for the longest. Azure and GCP have their own function runtime environment. One thing you'll notice when using these like runtime environments is that you'll run into vendor lock-in issues. So in order to avoid this, a lot of open source projects exist that expose a common framework that you can tap into to make your serverless applications. On the JavaScript side, you have Serverless, or SLS. That supports Azure, AWS, GCP, along with a lot of other serverless runtimes, and it works pretty well for JavaScript-based services. With Python, you have Zappa. And if I'm being honest, the first time I saw Zappa, I instantly knew I was going to love it. Zappa allows any Python developer to turn their Flask, Django, or Bottle apps directly into a serverless app. Currently, it only supports AWS, but hopefully in the future, they're going to support more cloud providers. Okay, so that's enough understanding about what serverless is. Let's talk about a quick hypothetical scenario. So imagine one day, you want to start a fun company with you and a friend. You decide to call the startup Suber, obviously no relation to the ride-sharing company. Suber specializes in giving rides as a service in submarines all around the world. So in order to start the company off right and quickly, you code the application in Django and deploy it to an EC2 instance running in the cloud. An EC2 instance is basically just what a VM AWS calls. A few months pass, and it turns out nobody's really using Suber. I guess the market for rentable submarines just isn't that big. The $100 per month you've been paying to Amazon for the EC2 instance has just gone to waste. But you decide to keep this running just in case people start to use the service. A few weeks pass again, and you receive a really exciting email. Suber has been accepted into Y Combinator, and it's being published about in all the hottest newspapers, tech blogs. It's on the top of Hacker News, and it's on the top of Reddit all at the same time. Suber's just exploding. But you go back to check and see how your EC2 instance is doing to hold up against this traffic. Oh no, it's completely crashed. You don't have any traffic. All the people are just running into tons of errors across all your APIs. You try to scale up the instance to one that's $10,000 per month and has a terabyte of RAM, but it's just not enough to hold the fort down. You add in Cloudflare for caching, but your API is just slowing the entire application down. You miss all the potential traffic and Super is dissolved as a company. Okay, well let's try again Super with some serverless programming. So this time when you deploy Super with Django, you're choosing to deploy it with AWS Lambda and the Zappa framework. It still doesn't get any initial customers, but once there is that huge surge of traffic, it's still okay because Lambda is taking care of the horizontal scaling for your application that everyone is still able to log into the application and use it. So everyone is so impressed with your sub-sharing site that you become a billionaire and buy a private island in the Caribbean where you never have to think about code again. Won't that be awesome? So the Super example really shows us what the pros of serverless deployment are. Serverless deployment comes with huge billing benefits. Not only did you not pay for much when nobody was using your site, you didn't have to scale it to a ridiculous EC2 instance just to handle some new traffic. Lambda did all of that for you in the background while still minimizing your cost. In the months nobody used Super, the AWS bill was less than a few dollars, and once people actually started using it a bunch, the bill is still pretty manageable. The biggest advantage with serverless programming we're seeing is horizontal scalability. As we saw with Super, you don't need to put in any extra effort to get that beautiful horizontal automatic scaling. Furthermore, because a lot of the stack was abstracted away, you didn't need to worry about how the code is hosted. You don't have to worry about whether Nginx is correctly configured, if it's up to date, if there's any 0 days available, because hopefully the cloud provider you've chosen is doing a good job at managing that for you. But serverless really isn't all benefits, and anybody who tells you that is just lying to you. Every single abstraction is going to come with downsides. Specifically for serverless, you're going to lose a lot of the control you get over the stack. So for example, if you have a magical patch to the Python runtime that is able to speed it up by like 2 times the speed, but it's not getting merged into upstream Python anytime soon, you're not going to be able to use this for your serverless application because you're stuck with the runtime that your cloud provider is providing for you. Furthermore, the performance story that serverless offers isn't always perfect. The scaling algorithm that cloud providers use is usually proprietary to their own service. So if you don't like the strategy they're adopting for scaling, you don't really have much ability to change it or modify it to your needs. Also, the instances that are serving your code are also limited in the specs that they can have. In AWS, this is a limitation of about 3 gigs of RAM and 512 megs of temporary disk storage space. Specifically for AWS, their deployment packages are usually limited to half a gig. So if you were thinking about serving that hot new machine learning algorithm that fits in a gig of storage, you're not going to be able to do that on a serverless platform. As a general side note, some of these limitations vary from provider to provider, so you're going to need to do your own research and determine whether that provider will be right for you based on their instance sizes. And now we have to confront the elephant in the room. Cold starts are really hard with serverless programming. Basically, whenever your application goes unused for a period of time determined by the cloud provider, your application, the instance that's serving your application will be shut down in order to conserve their cost. So upon the next invocation, the cloud provider will once again start your app from a cold state, which is going to increase the latency of that start. This time usually depends on the bundle of your code and what language you're using to code it in, but I've seen it to be around 2 seconds per cold boot. And if end users are querying these APIs, that could lead to a pretty poor user experience. Now there are ways to avoid this by using like scheduled tasks to keep your instances warm, but you have to pay an increased cost in your serverless work environments in order to avoid this cold start issue. But it's not exactly a huge hit. And we're going to discuss more about this in some future slides. All right, that's enough theory. Let's actually look at some cool implementations of a serverless function. For this demo, I chose to create a really simple API that allows users to crack 3-character long MD5 hashes. It's done with brute force, so we're not using any rainbow tables or pre-cached computations. In other words, we're assuming that the hashes are salted with a known salt. I'm not saying this code is efficient at all, and it should never be used in production because it's really slow, but it's an example that shows how powerful serverless is. I'm exposing the API over Flask, and I'm using Zappa for the Lambda deployment. So I'm going to first start this off by just starting my normal Flask app. It's really simple. It's just like 15 lines of code. And then I have a second compute script that allows me to test any API that I have exposed. So I pass in what endpoint that I want to hit with my API tester. And right now, I'm just going to query right directly to my laptop. And so we'll see that once the query finishes, it takes about 1 second to break 1 hash, which is not bad. And now we're going to try running the same script, but instead run it 10 times. This is taking about 6 seconds on my laptop. Now for the next experiment, I'm going to hit the API that I have deployed in the cloud. Once again, as I mentioned before, it's the same exact code. It's just deployed using AWS Lambda and the Zappa framework. Once it finishes the computation, you'll see that this actually ran a little bit slower than on my laptop. That's partly because of the cold start cost I'm paying on the first execution of the API. AWS needs to boot the instance that's running this API in order to serve the request from my local script. Also, the compute script uses randomized test cases, and I got kind of unlucky with my test cases, but we don't have to mention that part. So now that our function's warmed up, let's try something interesting. Let's try to break 1,000 hashes. So I'm going to attack the API with 200 concurrent requests, and you're going to see that once the script finishes, it does this super fast. In total, it's going to take 21 seconds to break these 1,000 hashes, and this is with changing literally nothing with my code. AWS is just scaling out all these instances for me invisibly. This really shows the power of the horizontal scaling AWS Lambda is offering to the application I've deployed. What took 6 seconds to compute 10 times on my laptop was computed 1,000 times in the cloud in less than 20 seconds. As a comparison, if I tried to compute these 1,000 hashes on my computer, it'd take a total of 10 minutes. And would you guys really enjoy watching me compute 1,000 hashes for 10 minutes in this demo? No, that's why we have to use serverless. So all in all, we went through 1 billion hash combinations in 20 seconds. Let's quickly discuss about what exactly made it faster. When I was testing the API locally running on my computer, I had my compute Py script call the API running on the local Flask instance on my laptop. I wasn't pulling any concurrent responses because my Flask API does not serve concurrently. It's blocked by any other previous request. After I switched to calling the API in the cloud, it started spawning more and more instances to serve the API request. Specifically, I told my compute script to concurrently call the API 200 times. Then AWS invisibly scaled the number of instances running the script in hopes to serve the traffic I was driving from my computer. This is known as horizontal scaling, where we increase the number of instances running our code. From what I'm aware right now, Lambda doesn't attempt to do any vertical scaling, which is what we tried with Scuba and increasing the amount of RAM we get for the application. It is only attempting a horizontal scale-out strategy. So how much money did I just waste during that demo? It must be a ton, right? No, it's actually a super small amount. Conveniently, it just fits into the free tier of AWS, but if it didn't, it would be a whopping 3 cents to run that entire experiment to compute hashes 1 billion times. AWS specifically bills by the gigabyte seconds you use during the computation of your script. From some calculations, I used about 1.7 terabyte seconds, and that equates to 3 cents of cost. And the time I spent writing that out was actually very short. It only took about 10 minutes to write out the Flask API and 10 minutes to deploy with Zappa. If I tried doing that with like VM scale sets, trying to deploy in Kubernetes with like automatic scale out, it would have taken way longer. But the power of serverless just allowed me to do that in less than 20 minutes. It was a super easy project. Now that we've seen a good implementation and usage of serverless design, let's look at a scenario where serverless didn't really work that well. As I explained at the beginning of this presentation, during the summer, I got to work with the local business as a full-stack developer. During that time, I was talking with the business development team at the location about how the IT team could help support the business as it grows. You see, the business was using a very legacy application programmed in PHP. I don't know what that is anymore. And it was slow to respond to like any application. Furthermore, other more legacy systems were integrating with that business app and sending bursts to that API that were slowing down the application for everybody. Because of this, end users were having a very bad experience with the entire business app. So I sat down with a team of 4 developers and we started rewriting this backend in a more modern stack with JavaScript and TypeScript. After writing the app though, we realized serverless might be a good choice to use with the backend. We were motivated to adopt a serverless design because a lot of the API queries that were like hitting the backend were event-driven and they required horizontal scaling for the processing. The legacy systems would get an influx of data and start hitting the business app directly, and because of that slowdown, we thought that implementing this in a serverless design would allow invisible scaling in the backend to help alleviate the issues we were facing. Also, during the day, the business app sometimes goes unused, but then at other times, the users just flood onto the system, once again hammering the slow server running the backend. Going by this, we could theoretically reduce our hosting costs by a lot if we went with the consumption style plan of serverless programming. So, like any modern development shop, we started work with a JavaScript-based backend deployed to the one and only AWS. But this is where we ran into some issues. Once we had deployed to a serverless backend, users were having really bad cold starts on the UI. And because we had gone with the microservice style of deployment, we were not able to keep all the lambdas warm with like the repeated invocations, as that would increase our AWS bill a lot. Also, every single time a user queried the serverless endpoint, those invocations were pretty slow because we weren't caching the connections to our SQL server running on premises. And so every time there was a request to the API, we would have to reconnect to the SQL server. Of course, there are ways to avoid this by spending some extra engineering time to ensure the safe management of all those connections. But being a small development shop, we didn't really have the time to go through this and actually adapt our code to the serverless environment. Another small issue we were running into was debugging. The debugging experience was just not as smooth as normal debugging experiences really are. Usually, local environment node debugs are very easy to do, they're quick to launch, but once we coupled that with serverless technology, we'd have to use like a Lambda emulator, which was slowing down development workflow and new things our developers just didn't know how to use right now. But we can't just consider the negatives of this serverless deployment. We should also consider the benefits. We were spending a lot less with this serverless style deployment instead of the VM we were using to host it before. Also, the event-driven API that was ingesting data from legacy systems was scaling really well, and we were experiencing no data loss, no retries, any of that stuff with the serverless backend. But these benefits, unfortunately, did not outweigh the issues that we were having. And this brings me to a really important point. Serverless isn't magic, and if you really think about it, it's not anything super new. It's just another abstraction in a world of abstractions that allows fast horizontal scaling and better billing models. Serverless is not going to solve all the problems from anybody, nor is it the perfect solution that everybody should just go and switch to right away. You'll need to really evaluate hot new tech individually in your own environment to determine if it's something that's going to benefit you and your development team, and if the benefits are actually going to outweigh the issues you might experience with this new technology. For our case, our solution ended up being to split out our backend into one that still processes our event-driven workflow in a serverless model and a user-driven backend to a slightly smaller VM in the cloud. So we were able to scale back the deployment resources that we were forcing for our user-driven backend, but still we were able to serve all the users pretty well. And so if you adopt new tech like serverless, you don't always have to go fully in. You can adopt some parts of it, and that's perfectly okay. If we had more time to engineer around all these limitations that we found with serverless deployment, it is entirely possible that we could have taken advantage of Lambdas for deployment. But this is something that we just don't have as a small development shop. Ironically, one of the benefits that serverless has is developers spending less time thinking about scaling operations. In some cases, that might be true, but for other cases, it just might not work out. If you choose to adopt serverless, you might end up spending more time engineering your solutions to work in a serverless style environment. And that's going to take away from you doing what you do best, writing code. So here's a different scenario. In this scenario, we have a school club at my local high school that everybody loves being a part of. And one of the things that we need to do for that is have our members sign up for events. So for this, we used to use something like a Google form to have students register onto these events, but we found that to be pretty hard to match with our workflow with cancellations and other logistic issues. So we thought, okay, let's write some code to automate this. So we went ahead and wrote a little small website in Django that helps students register for these events. And we deployed it to a VM in DigitalOcean, and it worked pretty well. But then we started having a larger amount of members join our club, and we were getting way higher request count. When event signups go out to our members, I was seeing our requests per second peak to 100 per second. So we started scaling up our VM. We were paying $30 per month at that point. And unfortunately, we don't have much money as students. We don't really have jobs. So instead, we thought, what else can we do to make this better? So we started considering a serverless model for our deployment rather than a purely server-based approach. Once again, we adopted the Zappa framework in order to deploy this to AWS Lambda, and we found this to be pretty advantageous. So horizontal scaling worked very well for this scenario because cold starts were not as perceived as an issue from users. It would only happen about 2 to 3 times every time we sent out a link to sign up to new events. And the cold start boot times we were observing were about 1 to 1.5 seconds. And we also had really good cost savings. We were no longer paying for the idle time of the application when users aren't signing up for events and people aren't going on the website. So in total, after deploying this serverless website, the total bill we had to AWS was 10 cents or something. It was really small. And also, the amount of time we spent writing code, figuring out deployment strategies, configuring VMs was so little because it was just one command from the terminal. So what are some takeaways from this presentation? Serverless is not a be-all, end-all solution for everything. It's really good in the case you need fast horizontal scaling or event-driven processing. Serverless programming also tends to encourage vendor lock-in. So whenever you try considering to move to a serverless model, modularize your code so that it can easily be adopted to another vendor's serverless design. In cases for backends where serverless is a good tool to use, but it's just not working for everything, it's okay to split it out into one backend that's serverlessly deployed and one that's normally deployed. This is only going to be possible if you modularize your code and write it in a way that you can still run it locally, but also deploy to the cloud in a serverless framework. Conclusion, serverless programming, all hype. Are there benefits? Of course there are benefits. We saw with the hash cracking API that we calculated 1 billion hashes in the cloud in a few seconds. But these benefits don't come without significant drawbacks. These drawbacks include extra engineering time you're spending adapting your code to the serverless design. It could be cold starts. It could be regulatory compliances where you're not able to use serverless design features. And so ultimately, I hope that you'll take this talk, and if you want to adopt serverless in your own environment, I wish that you put in the effort to determine if serverless deployment is going to be a beneficial technology for you in terms of engineering time, deployment cost, or end user experience. By spending the time, you're going to be able to verify that this is the right tool for you and not just some random presenter telling you about it at PyTexas. spend the time, figure out if it's really good for you, and then hit me up on Twitter and let me know what you thought and if serverless was successful for you. So thanks for listening. I have my information available. And I am open for internships if anybody would like to hire me. Thank you.